Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be covering current and potential difference. So when we talk about current, we're talking about the flow of electrons through a wire, and we can talk about this and compare this analogously to the flow of water or the rate of water flowing through a stream. So when we're talking about electrical current, we're talking about the flow of electrons. We're talking about a current in a stream. We're talking about the flow of water, and so we can use the flow of water in a stream as an analogy to the flow of electrons through a wire. And so let's begin by talking about our unit ampere. An ampere, or just an amp, that's going to be the measure of electricity or electrical current, and that is defined as 1 coulomb per second. So if you have 1 amp of current, that's 1 coulomb of charge per second. Okay, so that is the measure of the current. And so when we're talking about currents, we want to ask the question: what is the driving force? What's driving the current? What's causing the current to or the substance to flow, or whatever we're talking about? And in this case, when we're talking about water current, this water current is driven by the difference in gravitational potential energy, which is caused by a gravitational field. And so you have this difference in gravitational field, and so this is going to cause the flow of water. So water in a stream is going to be flowing downwards. So it's going to be traveling from a higher place to a lower place, a place of higher gravitational potential, and it winds up reaches a lower gravitational potential. So it's going to flow in that direction. So similar when we talk about electrical current is also driven by a difference in potential energy, and this difference in potential energy is called the potential difference. And just like the difference in potential energy, gravitational potential energy, this difference in potential energy is caused by an electrical field instead of a gravitational field. So then this is going to result from this electrical field results from the charge difference on the two electrodes in our cell. So if you remember from the previous video, I had a picture of a cell where you had the one beaker with 1/2 reaction. That's the reaction where you had, say, oxidation, the oxidation reaction occurring, and then the other beaker you had the reduction reaction occurring, and you had the electrodes in each of the beakers connected to a battery, or it could be connected to a motor. And so, because of the electrical difference between the two electrodes, that's going to cause the electrons to flow from one electrode to the other. And the electrons are going to flow in such a way that they're going to go from a higher potential to a lower potential. And so, we'll talk more about that in a later video. So, what is the potential difference? The potential difference is the measure of the difference in the potential energy, which is usually in joules, per unit of charge, which is in coulombs. And so, so when we talk about the difference in potential, the unit that we're using is the volt. So 1 volt is defined to be 1 joule of energy per coulomb. So the voltage, when we're talking about voltage, we're talking about what's that difference in energy between the electrodes. So a potential difference of 1 volt. So what does this mean? This means that a potential difference of 1 volt indicates that a charge of 1 coulomb experiences an energy difference of 1 joule between the electrodes. So what does that mean? That means a larger potential difference means that you have a larger difference in charge between the two electrodes. So this is kind of like if we compare this to how fast water flows in a river, well, that's going to depend on the steepness of the riverbed, right? So the more steep the riverbed, the more it's going to flow there. So you have a greater flow. So if I have a riverbed that's kind of steep this way, the river is going to flow more quickly down. And so there's more of a gravitational force acting on the water. And so, in the same way, when you have a larger difference in the charge between the electrodes, the larger that difference, the more that you're going to have a force on the electrons that's going to go push the electrons from one electrode to the other. And so that the greater that electrical difference, the greater that charge difference between the electrodes, the more force that the electrons are going to feel, the faster it's going to flow. And so this is why when we talk about potential difference, we also refer to it as the electromotive force. So these are interchangeable. So the potential difference is the electromotive force, or EMF. And so when we're talking about this EMF and all of that, then what we want to do is think about this. How does this apply to, say, the voltaic cell that we were just talking about in an earlier video? Well, that's next. So if you just wait right there, we'll go on to that part. Okay, so what about a voltaic cell? What are we talking about there? How do we apply this to that situation? So when we're talking about a voltaic cell, when we talk about the potential difference between the two electrodes, we actually call that the cell potential. Cell, because cell is another name for battery, and that's really what we're talking about when we're talking about a voltaic cell. And so we call that the cell potential, or it's expressed or abbreviated as E cell. Or it's also, as we said before, it could be called the cell EMF, which EMF again is the electromotive force. And so the cell potential is going to depend on a few things. The first thing it depends on is the relative tendencies of the reactants to undergo oxidation and reduction. So the stronger the tendencies that the reactants have to undergo either oxidation or reduction, the greater the cell potential. So if you have some reactant that it really wants to undergo oxidation, and you pair that up with another reactant that really wants to undergo reduction, then you put those together, there's going to be a larger cell potential. A couple of things that the cell potential depends on is the concentrations of reactants and products in the cell. We'll talk more about that later, but that's going to influence how large the cell potential is, and of course, temperature is also going to influence that as well. So let's talk about under standard conditions. So we always need to talk about standard conditions versus non-standard conditions. What are the standard conditions? As we said before, if you're in solutions, it's 1 molar is the standard condition. If you have gaseous substances, it's going to be 1 atmosphere. So when you're under standard conditions, as you could guess, the cell potential is now called the standard cell potential, the standard cell potential, or E cell with that circle. Remember, every time we see a circle up there, that means standard. So we saw that with standard enthalpy, standard entropy, standard free energy changes. Or it's also called standard EMF. Okay, so let's look at a couple of examples to clarify what we're talking about in this video. So here, excuse me, in a previous video, we talked about zinc solid being paired up with copper 2 ion. So here the zinc is going to transfer electrons. So here the zinc is going to be oxidized, and the copper 2 ion is going to be reduced. So you pair these up. Zinc is a relatively has a relatively high tendency to undergo oxidation. Copper has a relatively high um, tendency to undergo reduction. You put these together and you get zinc 2 plus and copper. And you'll notice that the standard cell potential is a positive 1.10 volts. Now, if we switch out the zinc with nickel, nickel doesn't have as high of a tendency to undergo oxidation. So what happens to the cell potential? So here we have nickel reacting with copper 2 plus to form nickel 2 plus ions and copper. And you'll notice that the cell potential for that reaction is a positive 0.62 volts. Now remember, the volt is a measure of the charge difference between the electrodes. So the larger that charge difference, the larger that cell potential, the more readily the reaction is going to occur. So this cell potential is a measure of the overall tendency of the redox reaction to occur spontaneously. So now we have another way of measuring the spontaneity of a reaction. So we can use cell potential to do that. So what does that mean? So you'll see that these are positive. What does a negative standard cell potential mean? That means that the forward reaction is not spontaneous. So the reverse reaction is the one that is going to be spontaneous. And so that is how we understand cell potentials in a voltaic cell. I hope this was interesting. I hope this was helpful in any way. If it was, please by all means share my video, like my videos, hit this like button right there, that like button down there. And also make sure you subscribe to my channel, hit that notification bell up there. Make sure that when you hit that notification bell, you hit the all so that way you can be notified by all my videos that I put out. And also, lastly, put a comment down in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.